Hello everyone. In this video, I'm going to explain how to solve separable equations. They are kind of the first class of first order differential equations that can be solved using integration. And here you get to practice some of the integration techniques in Calc 1 and Calc 2. All right. So that's a good idea to practice these using either appendix or previous notes that you have. Let's see what this is about. A little bit introduction, then kind of explanation to the process. Then we do examples. Then I go a little more into the examples. So if you have dy by dx equal to f of xy, then this can be written in a way to isolate the variables x and y kind of together with dx and dy on opposite sides. Let's just give you kind of first what it means. Let's say you can write it in a way that you have h of y times dy equal to g of x times dx. As you see, the variables are in opposite sides, they're not all on the same side. So that means these f of xy can be expressed as a g of x times some function 1 over h of y. And formally, in this formula of when you look into software and other places, usually it's looked as some function p of y. So function p of y is 1 of hy, which means this f of xy can be written as a kind of like a product of two functions, each one has its own variable. So this kind of just to bring us to a definition, which means if the right-hand side, so this f of xy, if the right-hand side of the equation can be written as a function of g of x that depends only, can be written, let's write it down, can be written as a function g of x that depends only on x. So see, depends only on x times a function p of y, right? That depends only on y, depends only on y. Then this differential equation is called separable, right? Then this dE, which we have, then this differential equation is separable, okay? So you're going to, of course, ask, give me a quick example. Here it is. Quick example. Let's say I have, and we're going to see examples where they may not look to be separable, but they are. So it is just like a quick thing. So 2x plus xy over y squared plus 1. Of course, if you look at this right-hand side, you can factor here and do x times 2 plus y and over y squared plus 1 And that kind of give you the idea to what g of x is, right? So g of x is this one, and p of y is this one, right? So you get g of x times p of y, where g of x is x, and p of y is 2 plus y over y squared plus 1. So for this, yes, it is. Let's give an example on no, something that it's not. dy over dx equal 1 plus xy. All right, so that's not separable. What is the method in doing these? So what is the method? It's going to be straightforward. Uh, let's say here it is dy over dx. You have it separable, or you made it separable here. Like that example, you factor so it is clear. Well, you're going to multiply by dx and 1 over py, all right, which is that was called in the introduction as a h of y. So you get some h of y times dy equal g of x dx. After you multiply, that's what you will get. Then, of course, you're going to integrate. Okay. You're going to integrate both sides. The left-hand side would give you some antiderivative plus a constant. The right-hand side that it's going to give you some antiderivative there and some constant. And as we saw, we can combine the two constants in some constant of differentiation. And we're going to call this the implicit solution. All right, implicit solution to this differential equation. And of course, here it is also a general solution. And if you run into initial value problem, you can use the conditions that you have of the initial conditions. All right, so let's do an example. All right, so solve this nonlinear differential equation. So you're going to get quickly used to it. So you're going to need to multiply by dx, right? Then 1 over py, 1 over py here, right? So when you multiply by dx, you're going to get dy equal x minus 5 over y squared dx. Then you're going to multiply by 1 over py, which is 1 over y squared py. So you multiply by y squared both sides. So you get x minus 5 dx. Then you're going to integrate both sides. And you expect, as mentioned, a constant here and a constant here, which you will combine both as one constant of integration. And so here, y squared, the antiderivative is 2 plus 1 is 3. There is no 3 there, so you do 1/3 for it to make up for it. And then here, x, so you will do the x squared, right? And also there is no 2 there, so you make up for it. and a 5x when you integrate 5 and negative 5. All right. So here we can multiply by 3 to get rid of these fractions here. So you'd have y cubed, 3 halves x squared minus 15x plus 3c. Again, we've done this a couple of times. This is 3c. It's also a constant. We can, if I called it here some constant c3 or whatever, right? I'll just do that here by combining c2 minus c1 that you get. You can return here and say, okay, this is c. This is a constant because 3 times a constant is a constant. And that will give you the next step, which is y cubed equal 3 halves x squared minus 15x plus, if you're instructed, let's say, in the software, sometimes you're instructed that, okay, use constant k or something like that, then you keep going, and that means here you're gonna replace it with whatever was indicated. So sometimes for the computer to understand the constant, you will need to use what's stated there. So here in that case, I'll just put k here. So we see that this is y cubed, so we need to take cube root to both sides, and that's going to give us the implicit form. And if you go here to Dismos and you type in the function, which is the solution, or this family of solutions, and as you see, just a little bit with practice, you start to see and learn how to do this stuff. This is one of the good tools online where now based on k, this constant, you can view in different ways, but usually it would give you a function and give you a kind of slider, and as you slide k, it will change the function. But if you do it this way, you'll be able to see this family of solutions. And each curve represents for some value, let's say negative 24, let's say here. This one here for negative 24, right? And this one here will be for k equals 0. Okay. And this is a representation to the example. Let's say now we want to solve this DE x y minus 1 over x plus 3. But now we're going to make it an IVP by giving it some initial condition. So now you start getting the feel for this. Multiply by dx, you would have a dx here, both sides, and then multiply by 1 over y minus 1. 1 over y minus 1 will give you y over y minus 1 here. Okay, so multiply by dx. This dx is out on the left, shows up on the right. Multiply by 1 over y minus 1, right? This y minus 1 is out from the right side, and it shows on the left side. After that, we do integration. And you know, when you integrate 1 over, let's find it again. 1 over y minus 1, that's going to be a natural log of absolute value of y minus 1 equal to natural log of x, absolute value of x plus 3, plus the constant. Then you're going to solve this logarithmic kind of equation. So you're going to take e to both sides. And that's going to give us the absolute value of y minus 1 equal the absolute value of x plus 3. Because here, when you do it, you're going to get, for this part, let's show it here, you're going to get e, the absolute value of x plus 3, plus c, which is e, the natural log of x plus 3 with the absolute value times ec. Okay. For this right side, which we did a few examples. So times the constant here. This, you know, when you remove the absolute value, this is going to be interesting, something that maybe you haven't seen before. We're going to use here. You've seen some of it, but this takes it to another level. So, you know, absolute value of, let's say, x equal 5. That means x is 5 or negative 5. Something like that. So here, when we remove the absolute values, that means this is, we can replace this by another constant, let's say C1. And if I want to remove the absolute value here from both sides, when you did this in algebra, you needed to have plus or minus on either side, then it's just plus or minus, right? So that means y equal 1 plus or minus this constant times x plus 3. Here, C1, we know it's positive, right? And we can go further because we have this plus minus. Let's see here. It's the usual this plus minus, and we have a constant c that is positive. So we can do a new thing we probably haven't done before, or if you did it, that's great. To simplify by, let's say, another constant k, but here it's, I'll write it down, arbitrary non-zero, of course, non-zero constant. So you have a C1 to be positive, but plus or minus changes the sign. Then you also you have x plus 3. So we can take care of all the sign issue by having some constant that will make up for that, and it can be positive or negative. And you'll see when you do the initial condition, it's just going to work out. All right, so here, so now y equal 1 plus k some x plus 3, right? It's the general solution. Let's put the initial condition, y of negative 1 equals 0. That means 0 equal in the general solution 1 plus k times negative 1 plus 3. That means k is going to be negative 1/2 when you solve this kind of linear equation there. So what is the solution for the particular solution to this problem, which is the solution for the IVP? It's going to be 1 minus k is to be negative 1/2 x plus. Okay, let's do a few more. Then I'll do another video for more examples that are maybe going in a higher level. But just let's show you that sometimes you're not gonna get more than what you want and you start looking into other formats. But let's just give you an example of that. It's always nice to have some solution, but sometimes it gets a little bit more difficult. And we need to recognize when that happens, that we may need something else. All right, so let's look at this one. Of course, we separate the variables here. Then we're gonna send this has the y to this side. Then we integrate. Even though it looks difficult, but you still see that you can integrate each one. So integrate cosine of y or dy, you get sine of y. Integrate e to the y, you get e to the y. That gives you on the right hand side, you get x to the sixth minus x squared, and one gives you x and constant. All right, so as you see here, this kind of implicit form, but although we kind of reach an impasse here. So we would like to have a solution with y explicitly, but we cannot, of course, at this point. So it's often that in the case of solving nonlinear first order differential equations, so we're going to say that we solve the equation, and we must on occasions to be happy if we have some implicit uh, format, and if we don't find an explicit format, you see here in this example, so it's okay. What else? I think I'll stop for this video here. Then I'll do another one with other examples of 2.2 that probably maybe include like integration by parts. Okay.